Tonight, we're going to explore one of the most quietly misleading pictures in all of modern science. The flat diagram of the solar system, the one you grew up with 8 planets tracing neat rings around the Sun: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Drawn on a single clean page, as if the cosmos agreed to lie down flat for our convenience. But the real solar system is not a page. It is a 3-dimensional structure that begins as a thin disk of planets near the Sun, thickens into a tilted belt of icy worlds, and opens outward into a vast spherical cloud of trillions of objects, reaching nearly halfway to the nearest star. The disk is only the inner layer. The sphere is the true shape. And the words above and below, the ones we use so casually, turn out to describe nothing in the cosmos itself. Only our choice of where to stand. By the end of tonight, you're going to understand how the solar system transitioned from a protoplanetary disk 4.6 billion years ago into the layered geometry we see now. Why the ecliptic plane is a human reference frame rather than a cosmic one, and what it means to live inside a structure that has no true up and no true down. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The diagram starts early. Long before you know what a solar system really is, someone hands you an image. The Sun sits at the center. 8 planets stretch outward in a line. Mercury is closest, then Venus, then Earth, then Mars, then a gap, then Jupiter, then Saturn with its rings, then Uranus, then Neptune at the cold outer edge. Everything sits on one flat plane, arranged like coins laid out on a table. Maybe the image is a poster on a classroom wall. Maybe it is a page in a textbook, or a graphic that spins slowly at the beginning of a documentary. The specific form changes. The impression never does. That impression is flatness. One level, one plane, everything neatly aligned. And here is the quiet problem with that image. It is not exactly wrong. The planets really do orbit close to a common plane. The diagram captures something real, but it produces a false confidence about what the solar system looks like in 3 dimensions. If you carried that image in your head and asked what would happen if you flew directly upward, perpendicular to that plane, the image implies an answer. You would exit the system almost immediately. You would pass through a thin disk and come out the other side into empty space. The solar system in that picture is essentially flat. It is not. The rest of this journey is about showing you why, not in one step, in layers. Because the gap between the flat diagram and the real 3-dimensional structure of the solar system is not a small correction. It is a completely different picture. But here's where it gets strange. The diagram doesn't even get the planets right. Every one of the 8 planets orbits in a slightly different plane. The technical name for how far a planet's orbit tilts away from a reference plane is orbital inclination. Think of it this way. Imagine stretching a flat hula hoop around a lamp. The hoop represents Earth's orbit, and the lamp is the Sun. That hoop defines the reference plane, the flat ring that astronomers call the ecliptic. Now imagine another hula hoop, also around the lamp, but tilted, tipped slightly, so that one side rides higher than the reference hoop and the other side dips lower. The angle of that tilt, measured in degrees from the flat reference hoop, is the inclination of that orbit. 0 degrees means perfectly flat. 90 degrees would mean the orbit runs straight up and down, perpendicular to the first hoop. Earth's inclination is 0 by definition. The ecliptic is defined by Earth's orbit. So Earth is the baseline. Everything else is measured against it. And everything else tilts. Venus tilts about 3.4 degrees. Mars tilts about 1.85 degrees. Jupiter, despite being the largest planet in the solar system, tilts only about 1.3 degrees. Saturn comes in around 2.5 degrees. Uranus tilts about 0.8 degrees. Neptune tilts about 1.8 degrees. Those numbers sound small, They are small. But small degrees translate into very large distances. And this is where the flat diagram starts to break down, even at the level of the planets. Mercury is the most extreme case among the 8. Its orbital inclination is roughly 7 degrees. 7 degrees sounds almost trivial. A barely perceptible tilt. But think about what 7 degrees means when the orbit spans tens of millions of kilometers. At the most extreme points in its path, Mercury can sit about 7 million kilometers above or below the ecliptic plane. 7 million kilometers. To put that in physical terms, the Sun's diameter is roughly 1.4 million kilometers. So at its greatest deviation, Mercury sits nearly 10 times the Sun's diameter away from the reference plane. Not slightly off the flat plane, dramatically off it. Wait, the diagram shows Mercury as a dot on a line. It is actually tracing a path that swings nearly 10 sun widths above and below that line over the course of its year. The diagram has already lied to you. Not about something exotic at the edge of the solar system. About the closest planet to the Sun. So why do the planets tilt at all? If they formed from the same flat rotating disk of gas and dust, shouldn't they all share one plane exactly? They should. And when they first assembled from that disk, they came very close. But the early solar system was not a quiet place. It was a system of collisions, close approaches, and gravitational chaos. Protoplanets formed and shattered and reformed. Gravity between those growing bodies pulled orbits out of alignment. Jupiter, by far the most massive planet, exerted the strongest influence. Its gravity reached across the forming system and perturbed everything around it, nudging orbits slightly out of the shared plane. Then something larger happened. Scientists call it the Nice model, named after the city of Nice in France where the theoretical work was developed. The Nice model describes a period early in the solar system's history when the giant planets were packed into a more compact region much closer to the Sun than they sit today. Jupiter, Saturn, Uranus, and Neptune were closer together and closer in. Over time, gravitational interactions between those giant planets and a vast outer disk of smaller icy bodies drove a reshuffling. Jupiter migrated slightly inward. Saturn, Uranus, and Neptune migrated outward. Uranus and Neptune may even have swapped their positions during this period, with the planet we now call Neptune briefly closer to the Sun before the two exchanged places. That reshuffling sent ripples through every orbit in the solar system. Inclinations shifted. Orbits that had been nearly flat took on small, persistent tilts. The chaos of that era is written into the numbers we measure today. Mercury's 7 degrees, Venus's 3.4 degrees, Saturn's 2.5 degrees. Each one is a relic, a surviving imprint from a period of violence that ended billions of years ago, and left the solar system looking, at first glance, almost perfectly flat. Almost. Today's near flatness is not a sign that the solar system formed peacefully and stayed that way. It is what chaos looks like after it has mostly damped out but not completely. The small tilts are what survived. The solar system you see in the diagram is a system that has been through enormous disruption and settled into something that resembles order without quite achieving it. Even the 8 planets, the objects shown in every schoolbook diagram of the system, do not orbit in a single plane. They orbit in 8 slightly different planes, each one tipped by a different angle, each one carrying its planet above and below the ecliptic in a slow, repeating cycle. The flat image in your head was never quite accurate, even for the most familiar part of the system. And the planets are only the beginning. But before we catalogue more of those failures, there is a stranger question underneath all of this. Why is the solar system flat at all? The answer reaches back 4.6 billion years, before the Sun existed, before any planet existed, before there was anything to draw a diagram of. What existed then was a molecular cloud, a vast, slowly drifting body of gas and dust, mostly hydrogen and helium, with traces of heavier elements scattered through it: carbon, oxygen, silicon, iron. Those heavier elements were not original to the universe. They were seeded into the cloud by earlier generations of stars. Stars that had lived and died before our Sun was born. scattering the material of their cores into space through stellar winds and supernova explosions. The molecular cloud was, in a sense, the accumulated inheritance of everything that had come before. It spanned light years. It held enormous amounts of material. And it was, for a long time, roughly stable, held in balance between the inward pull of its own gravity and the outward pressure of its own internal gas. That balance did not last. Something triggered a collapse. Scientists are not certain exactly what it was. It may have been the shockwave from a nearby supernova, a pulse of energy powerful enough to compress part of the cloud past the threshold where gravity could take over. It may have been the gravitational tug of a passing star. Whatever the trigger, part of the cloud began to fall inward. Gravity was winning. Here is what scientists believe happened next, and here is where the physics becomes something you can feel intuitively. The cloud was not perfectly still before the collapse. Nothing in space is. It had a slight, slow rotation, a gentle spin, probably imperceptible over human timescales. That rotation was important. As the cloud collapsed inward, that rotation did not disappear. It could not disappear. A law of physics called conservation of angular momentum prevented it. Angular momentum, the quantity that describes how much rotational motion an object has, is conserved. It does not vanish. When an object shrinks, its rotation speeds up to compensate. Think of a figure skater. She begins a spin with her arms extended, rotating slowly. She pulls her arms in toward her body. She does not apply any new force. She does not push off the ice again. But her spin accelerates dramatically, faster and faster, until she is a blur. The rotation was always there. What changed was the distribution of her mass. Concentrated inward, the same angular momentum produces a much faster spin. The collapsing cloud did exactly this. As it shrank from light years across towards something far smaller, the slight pre-existing rotation amplified. The cloud was spinning faster and faster as it fell inward. And that is when the shape changed. A spinning, collapsing cloud does not collapse uniformly. Gravity pulls inward from every direction equally. But the spin resists collapse along one axis. Think of tossing and spinning a ball of pizza dough into the air. Gravity pulls it downward. The spin stretches it outward along its equator. The result is not a sphere. The result is a flat disk. The material that could collapse inward along the rotational axis did collapse. The material being flung outward by rotation could not collapse as easily in that direction, so it spread, flattening, settling into a rotating plane, not by accident, not by design, by physics. The dense, hot concentration at the center became the sun. The remaining material, still orbiting, still spinning in that flat disk, became the protoplanetary disk. A vast rotating plate of gas and dust stretching outward from the young sun. And this is where planets come from. Not from the sun directly, from the disk around it. Inside the disk, small particles of dust began to collide and stick together. Dust grains became pebbles. Pebbles became boulders. Boulders collided and merged into kilometer-scale objects called planetesimals, the building blocks of planets. Planetesimals continued to accumulate mass, their gravity growing stronger as they grew, pulling in more material. They became protoplanets. Protoplanets swept up the remaining material in their orbital paths and became the planets we know today. Every step of that process happened inside the disk, inside the flat, rotating structure that the spinning cloud had created. The planets did not drift in from random directions. They did not form at arbitrary angles. They grew in place, inside a structure that had a single, well-defined plane of rotation. And this is why the flat diagram has merit. Not because someone decided it was convenient, not because it makes textbooks easier to print. The planets orbit in roughly the same plane because they formed inside the same flat disk. They inherited its orientation. The flatness is not a simplification. It is a memory, a physical imprint of the process that built everything in this system. The shared plane they orbit in has a name. It is called the ecliptic plane. The ecliptic is defined specifically by Earth's orbit, the plane the Earth traces around the Sun each year. Every planet's orbital inclination, the number we measured in the first part of this journey, is measured as a tilt away from that plane. Mercury at 7 degrees, Venus at 3.4 degrees. All the rest, smaller angles still. Those small tilts exist because of the chaos we talked about earlier. The gravitational reshuffling, the collisions, the migration of the giant planets in the early solar system. But the tilts are small precisely because the original disk was flat. The violence of early solar system history moved the planets, but it could not move them far. The disk's geometry held. So the flat image you have carried in your head since childhood is not wrong. It is pointing at something real. It reflects a genuine physical process, the collapse of a spinning cloud 4.6 billion years ago, the conservation of angular momentum, the inevitable flattening of matter that spins as it falls. What looks like an artistic convention in a diagram is actually a compressed record of how the solar system came to exist. For the 8 major planets, the flat picture is a reasonable approximation. But the solar system does not end with the 8 major planets. Let's stay with that shared plane for a moment, because the name we give it hides something. We call it the ecliptic. It sounds solid, official, like something you could point to in space and say, there it is. But the ecliptic is not a physical surface. There is no wall there, no membrane, no floor. If you traveled to the ecliptic plane right now, you would notice nothing. You would pass through it without feeling a thing, because there is nothing to feel. The ecliptic is a mathematical definition, and only that. Here is how it is defined. Take Earth's orbit around the Sun. Trace that elliptical path until you have a closed curve. Now, imagine filling that curve in, the way you would fill in the outline of a drawing, and then extend that filled surface outward in every direction, forever. Infinitely large, perfectly flat, invisible. The result is the ecliptic plane. It is less like a floor and more like an infinitely large, perfectly flat, invisible tabletop extending outward from the Sun in all directions. Every point on that tabletop is, by definition, on the ecliptic. Everything above it is north of the ecliptic. Everything below it is south. But now a question. Which side is north? Here's the convention. Hold out your right hand. Curl your fingers in the direction Earth travels around the Sun, which is counterclockwise when viewed from above. Your thumb now points upward. That direction, the direction your thumb points, is ecliptic north. It points roughly toward the constellation Draco, the dragon, a long winding pattern of stars in the northern sky. The side of the ecliptic that faces Draco is, by convention, the north side. The opposite side is south. Above is north. Below is south. That is the system. It works. It is consistent. Astronomers use it every day. But the picture did not hold. That whole system, the north side, the south side, Draco as the reference point, none of it is written into the universe. We chose it. Every part of it traces back to one decision. We decided to define the reference plane using Earth's orbit. Not Mars's orbit, not Jupiter's orbit. Earth's. A resident of Mars would make a different choice. Mars's orbital plane is tilted 1.85 degrees from ours. Small enough that you might think it barely matters. But that small tilt means a Martian astronomer, using the same logic we use, would define a plane that runs at a slight angle to our ecliptic. Their north would point in a slightly different direction. Their version of the flat solar system diagram would look a little different from ours, and they would have no reason to prefer our definition over theirs. A resident of Mercury would go further. Mercury's orbital plane is tilted 7 degrees from ours. That is a substantial angle. A Mercurian drawing a map of the solar system would choose a reference plane running at 7 degrees to our ecliptic. Every measurement of every planet's inclination would shift. The whole picture would rotate. Neither of them would be wrong. That is the point. No one plane is physically special. Any planet's orbital plane is, in principle, a valid choice for a reference. We chose Earth's because we live here. That is the entire reason. This might feel abstract, so think about it closer to home. On Earth, up feels absolute. It feels like a fact about the universe, not a local condition. When you stand in New York and point up, you're pointing in a specific direction in space, away from the Earth's center, out toward the sky. When someone in Sydney stands up and points up, they are also pointing away from Earth's center, out toward their sky. But in terms of absolute direction in space, the person in New York and the person in Sydney are pointing in nearly opposite directions. Their downs, the directions their feet are pressing against the ground, point away from each other, diverging as they extend outward into space. Local up is not universal up. Gravity supplies a preferred direction locally, and we are so accustomed to that local direction that it feels cosmic. It is not. In interplanetary space, away from any large gravitational source, that local guidance disappears entirely. There is no up. There is no down. No direction is preferred. The universe does not come with labels. If you floated in the middle of the solar system with no reference and asked which way was north, the question would have no answer until you chose a reference. Then, it would have whatever answer followed from your choice. So when astronomers say a comet is above the ecliptic, they mean something precise. They mean the comet is on the same side of Earth's orbital plane as the constellation Draco, by a convention that traces back to the right-hand rule, which traces back to the direction Earth orbits the Sun, which traces back to the decision to use Earth's orbit as the zero line. It is a chain of choices all the way down. Here is a reasonable question. Is there a more principled choice, one not keyed to any single planet? There is. It is called the invariable plane. The invariable plane is defined using the total angular momentum of the solar system. Angular momentum is a measure of how much rotational motion a system contains, a quantity that accounts for the mass of every object, and how fast and how far it orbits. Add up the angular momentum of every planet, every moon, every asteroid, every comet. The plane perpendicular to that total is the invariable plane. It does not depend on which planet you happen to live on. It is, in a meaningful sense, a property of the solar system as a whole, rather than a property of any single orbit within it. The dominant contributor to that total angular momentum is Jupiter. Jupiter's mass is enormous, roughly 318 times Earth's, and its orbit is large. Those two factors together give it an outsized share of the system's total rotational budget. The invariable plane is pulled strongly toward Jupiter's orbital plane, but it also absorbs contributions from Saturn, Uranus, Neptune, and every other object with significant mass and a significant orbit. The result sits about 1.6 degrees from the ecliptic. Not 7 degrees, not 45 degrees. About 1.6 degrees. That small angle is telling you something. The inner solar system really is flat. The ecliptic and the invariable plane are very close to each other because the planets form together from the same rotating disk, and their orbital planes all stayed near that original geometry. Two different ways of defining the solar system's reference plane, one keyed to Earth, and one keyed to total angular momentum, and they disagree by less than 2 degrees. That is a confirmation of genuine physical flatness, but it is also a reminder that even the most principled choice is still a choice. The invariable plane is arguably more physically meaningful than the ecliptic. But the word above still has no meaning until you pick one of them and orient yourself against it. Above and below are not facts about space. They are facts about which frame you chose. And the frame we use, the ecliptic, the one built into every astronomy textbook and star chart and solar system diagram, is the frame of Earth. Our planet's orbit, our planet's direction of travel, our planet's local orientation, built into the definition of up and down for an entire solar system. That is the first layer of convention hiding inside words we use as though they were simply true. And the solar system has more layers still. So let us come back to something concrete for a moment. How flat is this disk exactly? When you actually measure it? The planetary region stretches from Mercury, at roughly 58 million kilometers from the Sun, all the way out to Neptune, at roughly 4.5 billion kilometers. That is a width of about 4.4 billion kilometers. And the maximum vertical excursion any major planet makes above or below the ecliptic is about 7 million kilometers. That is Mercury again, tilted most steeply of the 8. So the disk is roughly 4.4 billion kilometers wide and roughly 14 million kilometers thick, counting both the upward and downward reach of the most tilted planet. Think about what that ratio means. The planetary region is approximately 300 times wider than it is thick. 300 to 1. That is not just flat, that is extraordinarily flat. Here is an analogy that captures it. If you scaled the planetary region down to the size of a compact disk, the disk would not be the thickness of a coin. It would not be the thickness of cardboard. The thickness of the planetary region at that scale would be closer to a single sheet of paper, thinner than what you flip through reading. That is how extreme the flatness is when you measure it rather than imagine it. And this is why the 2D diagram works as well as it does. For the 8 major planets, collapsing everything onto a flat page loses almost nothing. The planets genuinely do cluster inside an extraordinarily thin band. The diagram earns its simplification for those 8 bodies. But something was wrong. The solar system is not 8 planets. It is 8 planets, and then billions of other things. Dwarf planets, asteroids, comets, icy bodies of every size scattered across distances that dwarf the planetary region itself. And those other things do not all behave like the 8 planets. Not remotely. Take the asteroid belt, the band of rocky debris orbiting between Mars and Jupiter. Millions of objects, ranging from dust to bodies, hundreds of kilometers across. Most of them orbit roughly in the ecliptic plane. But the inclinations in the asteroid belt are systematically, measurably higher than those of the planets. Many asteroids tilt at 10, 15, or 20 degrees. Some tilt at more than 30 degrees. The asteroid belt is not a single flat ring. It is a thickened, irregular cloud with objects scattered well above and below the plane the planets prefer. Look at specific cases and the numbers become striking. Vesta, one of the largest bodies in the main belt, has an inclination of about 7.1 degrees. That puts it roughly in the same league as Mercury, the most tilted of the 8 planets, already outside the neat story the standard diagram tells. Ceres, the largest body in the asteroid belt, and officially classified as a dwarf planet, has an inclination of about 10.6 degrees. That is tens of millions of kilometers of vertical excursion per orbit. Ceres regularly swings well above and below the plane that the 8 planets cluster near. It would not sit on a flat diagram without visibly breaking out of the band. And then there is Pallas. Pallas is a large main belt asteroid, one of the biggest, and it carries an inclination of about 34.8 degrees. At that tilt, Pallas swings hundreds of millions of kilometers above and below the ecliptic on every orbit. Hundreds of millions. Pallas would appear far off the page in any standard diagram scaled to show the planetary region. It would be an outlier so dramatic, it would immediately raise questions about why the solar system looks flat at all. But Pallas does not appear in most diagrams. Neither does Ceres, tilted as it is. Neither do most of the high inclination asteroids. They are simply left out, not omitted carelessly, silently excluded. The objects that would break the picture are the objects the picture does not include. Think about what that means for the image you have seen of the solar system or your life. The flat diagram is accurate in a narrow sense for the 8 major planets. But the moment you extend it to include the full population of small bodies that actually share this solar system, the flatness starts to dissolve. The picture was never a complete photograph. It was a filtered one, curated for the objects that cooperate with the story it wants to tell. There is an analogy that makes this visible. Imagine you photograph a city from above, but your camera can only capture buildings that sit on one particular street. The photograph would show a tidy line of structures. You might look at it and conclude that a city is essentially a line of buildings. But the city is not a line. You have produced an accurate image of one street, not an accurate image of the city. The diagram of the solar system does the same thing. It is accurate for the objects near the ecliptic, and it quietly erases everything else. But there is another layer to this. Even setting aside which objects get included, the flat diagram implies something that is not quite true even for the planets. It implies the ecliptic is fixed, that the plane Earth orbits in today is the same plane it will orbit in 1,000,000 years from now, or that it orbited in 1,000,000 years ago. It is not. The gravitational pull of the planets on each other, especially the enormous pulls of Jupiter and Saturn, causes each orbital plane to wobble slowly over time. This is called orbital plane precession. The ecliptic itself shifts, not dramatically, not in a single lifetime or 1,000 lifetimes, but over tens of thousands of years, the reference plane drifts. The flat diagram is a snapshot of one particular moment, presented as though it were a permanent truth. And if you extend the view further still, the Sun itself is not sitting still. The Sun orbits the center of the Milky Way at roughly 230 kilometers per second, tracing a vast path around the galactic core. And as it does not stay level with the galactic midplane. It bobs upward through the plane of the galaxy, and then downward, and then back again, on a cycle of roughly 60 to 70 million years. The solar system is not just a flat disk. It is a flat disk riding a slow wave through an entire galaxy. That is a different kind of flatness question entirely, and one worth returning to later. For now, the point is this. The flat diagram earns its reputation for the 8 planets, because those 8 planets genuinely do occupy an extraordinarily thin band. But the diagram purchases its elegance at a cost. It excludes the objects that would complicate the picture. It presents a snapshot as a permanent truth, and it hides the fact that even its own reference plane is moving. The solar system is flat, and the picture of a flat solar system is also, quietly, a choice about what to show. Those two things are both true at the same time. And the further out you look from the Sun, the more the second one starts to matter. And the further out you look, the more that second truth starts to take over. Step past Neptune, and the picture does not just bend, it shatters. There is one object almost every person learned about in school. Its name is Pluto. For 76 years, from its discovery in 1930 until its reclassification in 2006, it sat at the end of the planetary lineup, the 9th planet. The last dot on the familiar diagram. Small, cold, distant, but still on the line. Still flat. It was never on the line, not really. Not in any way the diagram was honest about. Here is what the diagram hid. Pluto's orbit is tilted at roughly 17 degrees from the ecliptic. That is more than twice Mercury's tilt. Mercury, which already swings nearly 10 sun-widths above and below the reference plane, was the most extreme example we used earlier to show how even the planets are not perfectly flat. Pluto is more than twice as tilted as that. Think about what that means in physical terms. At the farthest points in its orbit above and below the ecliptic, Pluto sits more than 1.2 billion kilometers from that reference plane, more than 8 times the distance from the Earth to the Sun, 8 times that distance straight up or straight down. The asteroid belt's Pallas, with its 34-degree tilt, reaches far off the plane too, but Pluto does it at a distance that makes the numbers feel different. 1.2 billion kilometers is not a wobble, it is a full departure. And here is what is important to understand about how Pluto moves through that space. It does not hover near the ecliptic and occasionally drift above or below it. It slices through the plane at a steep angle. Half of every orbit is spent above the ecliptic. Half is spent below. The plane itself is just the crossing point, the brief moment when Pluto passes through the reference surface that the inner solar system calls its home. Think of a hula hoop leaning against a table at a steep angle. The table is the ecliptic. The hula hoop is Pluto's orbit. The hoop crosses the table at 2 points on each revolution. But most of the hoop is not on the table at all. Most of it rises high above one side, dips far below the other. That is how Pluto moves. Not nestled near the flat surface, cutting through it. But here is where it gets strange. The flat diagram taught to schoolchildren does not show this. It cannot. A diagram drawn from above, looking straight down on the solar system, has no way to represent vertical distance. A body 1.2 billion kilometers above the ecliptic looks identical on that map to a body sitting directly on the ecliptic plane. So the diagram either omits Pluto entirely, or it places Pluto on the same flat line as the planets. Both choices hide the truth, not a small inaccuracy, a fundamental misrepresentation of where Pluto actually goes. The tilt is not the only way Pluto breaks the pattern. Its orbit is also highly stretched. The 8 major planets follow paths that stay close to circular. Pluto follows a path that is dramatically elongated. At its closest approach to the Sun, Pluto comes into about 4.4 billion kilometers. That places it inside Neptune's orbit. At its farthest point, Pluto swings out to roughly 7.4 billion kilometers from the Sun. The gap between those two distances is enormous, and because those distances are so different, Pluto's orbital period stretches to 248 Earth years. One Pluto year is nearly 2.5 human centuries. So when scientists in 2006 voted to reclassify Pluto as a dwarf planet rather than a full planet, one part of the reasoning was precisely this. Pluto's orbit did not look like the other planets. It crossed Neptune's orbit. It tilted steeply away from the plane. It moved like something that belonged to a different population entirely. And it did. Pluto was never an outlier accidentally. It was the first widely known member of a much larger group of objects, all sharing similar characteristics, all living in the region beyond Neptune. That group has a name, the Kuiper Belt. A vast population of icy bodies distributed through the outer solar system, many of them tilted, many of them on elongated orbits, collectively forming a structure that looks nothing like the neat flat disk the inner solar system diagram suggests. Pluto was the signal, the first object well known enough to enter the cultural imagination that actually lived in this outer region rather than on the planetary line. For 76 years, it was classified as the final planet, and the flat diagram absorbed it into the flat story. When astronomers looked more carefully and reclassified it, part of what they were acknowledging was something the orbital geometry had been trying to say all along. Past Neptune, the rules change. The flat diagram had been hiding that. It had been placing Pluto on the line, labeling it the 9th planet, and implying that the outer solar system followed the same geometry as the inner one. It did not. Pluto's orbit was a first glimpse of a region where inclinations steepen, orbits stretch, and the tidy picture earns its first real fractures. And Pluto, for all its fame, is one of the smaller members of that outer population. The Kuiper Belt contains hundreds of thousands of objects. Some are larger than Pluto, some have tilts steeper than Pluto's, and the Kuiper Belt is only the beginning of what lies beyond Neptune. Follow Pluto outward, past the orbit of Neptune, and the solar system does not end. It widens, it deepens, it becomes something the flat diagram never prepared you for. For most of human history, astronomers assumed that whatever lay beyond Neptune would be sparse, a thinning remnant, the last faint edge of a disk that had been growing emptier with distance since the beginning. That assumption made sense. The planetary disk was flat. The region beyond it should follow the same logic, slowly fading into nothing. It does not. Immediately beyond Neptune's orbit, something unexpected happens. The disk does not thin. It thickens, dramatically. The geometry changes from a flat sheet into something far larger and more complicated. The structure astronomers eventually found that has its own name, its own subpopulations, its own architecture, and it bears almost no resemblance to the orderly flat ring most people picture when they hear the word belt. The Kuiper Belt extends from roughly 30 astronomical units, the distance where Neptune orbits, out to approximately 50 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. So the Kuiper Belt spans a range from 30 to 50 times that distance. It is not a narrow ring. It is a wide, deep, populated zone. The existence of this region was anticipated long before anyone could prove it. In 1951, astronomer Gerard Kuiper suggested that a population of icy bodies might exist beyond Neptune, remnants from the early solar system that had never been swept up into a planet. For decades, the idea sat without confirmation. Telescopes were not powerful enough. The objects were too faint, too distant, too slow. That changed in 1992. David Jewett and Jane Liu, working with a telescope in Hawaii, found the first confirmed Kuiper Belt object beyond Pluto. It received the designation 1992 QB1, a small, dim, slowly moving point of light. But it was there, and it confirmed that Kuiper had been right. Since then, the count has grown to more than 2,000 known objects. But 2,000 is almost certainly a small fraction of what actually exists. Astronomers estimate that hundreds of thousands of Kuiper Belt objects larger than 100 kilometers in diameter are out there, most of them simply too faint and too far away to have been catalogued yet. Smaller objects, those beneath 100 kilometers, likely number in the trillions, not thousands, not millions, trillions. The Kuiper Belt is not a thin scattering of leftover material. It is a vast, densely populated reservoir, but the reality was different. The shape of that reservoir is nothing like the planetary disk. When astronomers began mapping the inclinations of Kuiper Belt objects, they found something the flat diagram had given no hint of. The orbits were not clustered near the ecliptic. They were spread across a wide range of angles, some tilted 5 degrees, some 10 degrees, some 20 degrees, some more than 30 degrees. The Kuiper Belt was not a flat ring at all. It was more like a thick donut, a puffy, three-dimensional shell of objects surrounding the outer solar system, with a range of inclinations that would look startling on any diagram honest enough to represent them. This is a fundamental structural difference from everything that came before it. The 8 planets occupy a region roughly 300 times wider than it is thick, nearly flat. The Kuiper Belt is nothing like that. Its vertical extent is not a minor wobble. It is the defining feature. And within that donut, astronomers found something even more surprising. Not one population, 2. The classical Kuiper Belt objects, sometimes called cubewanos, occupy a range of roughly 42 to 48 astronomical units, orbiting on relatively circular paths. But within that single distance range, 2 entirely different families of objects coexist. The first family is the cold classical population. These objects have low inclinations, generally less than 5 degrees from the ecliptic. They move in nearly flat orbits, close to the plane of the original protoplanetary disk. They look, in terms of their geometry, almost like a thin outer extension of the planetary region. The second family is the hot classical population. These objects have inclinations up to 30 degrees and beyond. Their orbits are steep, tilted far above and below the ecliptic. They occupy the same distance range as the cold classicals, but they inhabit a completely different vertical structure. The word hot here does not mean temperature. It refers to the orbital energy, specifically to how stirred up and dynamically excited these orbits are. The cold classicals are geometrically quiet. The hot classicals are geometrically wild. And the leading explanation for the difference is Neptune. When Neptune migrated outward in the early solar system, its gravitational influence scattered objects into high inclination orbits. Some of those scattered objects settled into the hot classical population. Others remained undisturbed, preserving the low inclinations of the original disk. The result is a layered vertical structure inside a single region. A thin sheet of cold classicals embedded inside a puffy cloud of hot classicals, all coexisting between 42 and 48 astronomical units. Not one disk, 2 distinct populations, sharing the same stretch of space, occupying completely different vertical positions. The flat diagram cannot represent either of them honestly. Then there is the second major subpopulation, the resonant Kuiper Belt objects. These are bodies whose orbital periods stand in simple mathematical ratios with Neptune's orbital period. Neptune orbits the Sun once every 165 Earth years. A resonant object might orbit once for every 2 Neptune orbits, or 3 times for every 4 Neptune orbits. The ratio is always clean and whole. The most famous example is Pluto. Pluto's orbit is in a 3-to-2 resonance with Neptune. For every 2 full orbits Pluto completes, Neptune completes exactly 3. This sounds like a recipe for collision. Pluto's orbit crosses inside Neptune's orbit, at its closest approach. 2 objects sharing a neighborhood, one of them periodically crossing into the other's path. It seems like disaster waiting to happen. But the resonance prevents it. Think of 2 runners on a track with different speeds. If their lap times are in a precise ratio, they never meet at the same point at the same moment. One runner is always lapping the other at a different position on the track. The rhythm keeps them apart. Pluto and Neptune are in that kind of synchronized rhythm. By the time Pluto crosses inside Neptune's orbital path, Neptune is always somewhere else. The resonance is not a coincidence. It is a long-term gravitational lock that has kept these 2 bodies out of phase for billions of years. Resonances like this are not rare in the Kuiper Belt. They act as shelters. An object in a resonance with Neptune can maintain a stable orbit, even when that orbit is steeply inclined, even when it is highly elongated, even when it would otherwise be too dynamically chaotic to survive over billions of years. The resonance provides a kind of gravitational scaffolding, holding unstable-looking orbits in place across timescales that dwarf human history. This is the Kuiper Belt in full. A thick, layered donut of objects spanning from 30 to 50 astronomical units. Cold classicals orbiting quietly in a thin layer near the ecliptic. Hot classicals rising steeply above and below, scattered there by Neptune's ancient migration. Resonant objects locked into precise rhythmic relationships with Neptune. Their tilted and elongated orbits protected by the same force that might otherwise destabilize them. Not a flat ring, not a thin disk, a genuinely 3-dimensional structure. The setup was simple. The region beyond Neptune should thin and fade, an outer edge of a disk that had been emptying since the beginning. The reality was the opposite. Not a thinning disk, a thickening one. A donut-shaped population with subpopulations at every inclination, layered vertically in ways the flat diagram was never designed to show. And even the Kuiper Belt, vast as it is not the outermost structure in the solar system. There are regions beyond it where the geometry changes again, in ways that are stranger still. There are regions beyond the Kuiper Belt where the geometry changes again, and the first of them begins right at the Kuiper Belt's outer edge. Not a gradual fade into open space, a transition into something wilder. The scattered disk is the name astronomers use for a population of icy bodies whose orbits bear almost no resemblance to the neat tilted rings we have been describing. These are not objects moving in gentle circles or modest ellipses. They were flung. That is the right word. Neptune's gravity reached them during the solar system's early reshuffling, and instead of sweeping them into a resonance or scattering them out of the system entirely, it bent their paths into something extreme, highly elongated, highly inclined, orbits that reach as close as roughly 30 astronomical units at their nearest point to the Sun, then swing outward to hundreds or even thousands of astronomical units at their farthest. Some of these objects spend the majority of their orbit billions of kilometers away from the Sun, in a cold darkness that no spacecraft has yet visited. The inclinations tell the story most clearly. Classical Kuiper Belt objects reach 30 degrees. Scattered disk objects routinely sit at 40 degrees. Some exceed 50 or 60 degrees. At that point, the orbit is nearly tipped on its side relative to the plane the 8 planets travel in. More than halfway from flat to perpendicular. The flat diagram has no mechanism to show this. A body tilted 60 degrees from the ecliptic cannot be represented honestly on any 2-dimensional chart drawn edge-on to the planetary plane. It simply disappears into the vertical dimension the chart refuses to acknowledge. Then the data shifted. Within the scattered disk, there is a body that became the most consequential discovery in outer solar system astronomy in decades. Not because of its size, not because of its orbit, dramatic as that orbit is, because of what its existence forced the International Astronomical Union to do. In 2005, astronomer Mike Brown and his team discovered a world beyond the Kuiper Belt. They named it Eris. It is a round, icy body, slightly more massive than Pluto and only slightly smaller in diameter. By almost any comparison that had mattered for the previous 75 years, Eris was a planet-caliber object. It had the mass, it had the size, but it also had an orbit that placed it firmly, unmistakably, outside anything the planetary framework had been built to accommodate. Eris's inclination is approximately 44 degrees. Think about what that means in physical terms. The 8 planets orbit within a disk that is roughly 300 times wider than it is thick. Eris's orbit is canted nearly halfway between flat and vertical. Picture a coin lying on a table. Now picture a second coin leaned against a wall at a sharp angle, its face pointing not upward but sideways, tilted so steeply that it nearly stands upright. Eris's orbital path moves something like that second coin. For most of its 559-year trip around the Sun, Eris sits not near the ecliptic, but far above it or far below it, tracing a path through a region of space that most of the solar system has never visited. The numbers clarify the geometry. At its closest approach to the Sun, Eris comes to roughly 38 astronomical units, just inside the outer edge of the classical Kuiper Belt. At its farthest, it reaches approximately 98 astronomical units, more than twice the average distance of Pluto, more than twice Pluto's distance, and it arrived there by climbing steeply above the ecliptic and then descending steeply below it on the return. Not a slight wobble, not a modest tilt. A sweeping angular departure from the plane that the solar system diagram treats as the floor of everything. The discovery of Eris made one thing immediately clear. Pluto was not a strange outlier that happened to be tilted. It was one of the less extreme members of a population in which extreme was ordinary. Pluto at 17 degrees was relatively tame. Eris at 44 degrees was closer to typical for scattered disk objects, and others in that population exceeded even that. This is what triggered the reclassification, not politics, not a bureaucratic decision. A geometric reality. Here was a body more massive than Pluto, on a more inclined and more elongated orbit, in a region where dozens or hundreds of similar objects likely existed. If Pluto was a planet, Eris was a planet. And if Eris was a planet, the solar system had many more planets yet to be discovered, each one found by expanding the catalogue of similarly extreme outer bodies. The alternative was to acknowledge that both Pluto and Eris belonged to a different category entirely. Dwarf planets, members of a scattered population, not survivors of a planetary formation process. In 2006, the IAU made that acknowledgement official. But the implications for geometry run deeper than the classification debate. The scattered disk is not a thin ring sitting near the ecliptic, like a slightly puffier version of the classical belt. It is a population dispersed across a vast volume of space, largely invisible because of the very way we search for it. Here is what scientists understand about observational bias and why it matters. Most sky surveys looking for outer solar system objects concentrate their time near the ecliptic. This is rational. The ecliptic is where the planets are. It is where comets tend to come from. It is where most small bodies have historically been found. But the scattered disk is precisely the population that is least likely to be near the ecliptic. Objects tilted 40, 50, or 60 degrees spend the overwhelming majority of their orbital period well above or well below the ecliptic plane. They cross through it briefly, twice per orbit, at the 2 points where their tilted path intersects the horizontal plane. For the rest of their 500-year orbit, they are somewhere the surveys rarely look. The catalogue of known scattered disk objects is therefore skewed in a specific and important way. We have found, predominantly, the objects that happened to be near the ecliptic when we were watching. The ones far off plane, which is most of them for most of their orbit, are simply missing from the count. Not absent from the solar system, absent from our records of it. What this means is that the true mass and population of the scattered disk is unknown. Current estimates almost certainly undercount it. By how much is an open question, but the structural bias is real. The solar system may contain many more large, tilted, extreme orbit bodies than any current catalogue reflects. The three-dimensional volume above and below the ecliptic, in the region from 30 to hundreds of astronomical units, remains largely unsurveyed. What lives there in the cold darkness far from the plane where we tend to look is still mostly uncharted. The scattered disk tells us this much clearly. The Kuiper Belt pushed the flat diagram picture until it broke. The scattered disk pushes further. At 44 degrees, Eris's orbit is not a variation on planetary geometry. It is a departure from it. At 50 and 60 degrees, scattered disk objects are orbiting the Sun in a direction more than halfway sideways relative to everything the 8 planets do. The solar system contains a population of bodies whose paths cross the ecliptic only briefly, spend centuries in the vertical darkness, and are largely invisible to us because we built our surveys around the assumption that the solar system was mostly flat. We built that assumption from the planets. The planets earned it, but past Neptune, that assumption collapses one layer at a time. The scattered disk is one of those layers, and the population we have catalogued is, almost certainly, the tame fraction. What lies beyond it is stranger still. Keep going further. Past the scattered disk. Past the region where Neptune's gravity still shapes anything. Past the zone where any known planet has any grip at all. There is a population out there that does not belong to Neptune's domain. These are the detached objects. Detached not just by distance, but by dynamics. Their closest approach to the Sun already sits so far out that Neptune's gravity cannot meaningfully reach them. Neptune did not fling them there. Something else did. Here is what scientists believed for a long time. The outer solar system, beyond the scattered disk, should gradually quiet. Objects should thin out. The influences shaping orbits should weaken with distance and eventually die away. What remained should be the most orderly, most undisturbed material in the whole system. In 2003, that picture changed. Mike Brown, Chad Trujillo, and David Rabinowitz discovered a small, reddish body moving through the deep outer solar system. They named it Sedna. At first, its distance alone was remarkable. Its closest approach to the Sun, its perihelion, sits at roughly 76 astronomical units. That is 3 times farther out than the farthest edge of the Kuiper Belt. Neptune, at 30 astronomical units, is entirely irrelevant at 76. Its gravity is too weak at that distance to shape an orbit. Neptune had nothing to do with Sedna's path, but something else was happening. Sedna's closest approach is only the beginning of its journey. Its orbit is extraordinarily elongated. At its farthest point from the Sun, its aphelion, Sedna reaches roughly 937 astronomical units. That is approximately 140 billion kilometers from the Sun. Light, which crosses from the Sun to Earth in about 8 minutes, would take more than 51 days to reach Sedna at that distance. And then, there is the time. Sedna takes roughly 11,400 Earth years to complete one orbit. That number is worth holding for a moment. Human civilizations have existed for something between 5,000 and 7,000 years, depending on how you count. A full Sedna year began before the earliest writing, before the first cities, before the invention of the wheel, and it has still not ended. When Sedna next returns to its closest approach to the Sun, whatever exists on Earth will bear almost no resemblance to what exists today. Not a slow orbit. A timescale that makes recorded human history look brief. Sedna's inclination is relatively modest at approximately 11.9 degrees. But at 937 astronomical units, even a modest inclination corresponds to an enormous physical departure from the ecliptic. The sheer scale of the orbit amplifies everything. But at 937 astronomical units, Even a modest inclination corresponds to an enormous physical departure from the ecliptic. The sheer scale of the orbit amplifies everything. So, who shaped this? Not Neptune, not Jupiter. The orbit is too far, too elongated, too divorced from anything the known planets can do. 3 candidate explanations exist, and none of them is settled. The first is a passing star. Early in the solar system's history, when the sun still lived inside a dense stellar nursery, a nearby star may have drifted close enough to gravitationally perturb objects in the outer cloud. A single close encounter, billions of years ago, could have redirected objects onto the wide, looping paths we see today. That encounter left no trace we can easily read, but the orbits themselves may be its signature. The second is the galactic tide. The galaxy as a whole exerts a gravitational influence on everything in the solar system. Not strongly, not quickly, but over billions of years, the slow, cumulative pull of the galactic disk above and below, and the mass of the galaxy's spiral arms sweeping slowly by, can nudge orbits. The galactic tide works on timescales so vast that it barely registers on human scales, or even planetary timescales. But across the full age of the solar system, it accumulates. The third is something still undiscovered. An unseen planet. A large, distant body whose gravity quietly herds these orbits into patterns we can detect, but not yet explain. That third possibility has a name, Planet 9, and it is worth setting aside for now, because it deserves a full account of its own. In 2014, astronomers Scott Shepard and Chad Trujillo added another member to the detached population. They found an object designated 2012 VP113. Its perihelion sits at roughly 80 astronomical units, just slightly farther from the Sun at closest approach than Sedna. Its semi-major axis, the midpoint of its elongated orbit, reaches roughly 265 astronomical units. Its inclination is approximately 24 degrees. On its own, a second detached object could be a coincidence. 2 could be a coincidence. But Sedna and 2012 VP113 shared something beyond their distance. Their orbital orientations clustered in a way that did not look random. Their orbits seemed to point in similar directions in space. A random distribution would not produce that. Something was grouping them. Not scattered randomly, pointed together. That clustering is what brought the Planet 9 hypothesis to serious attention. But before reaching that, it is worth understanding what these 2 objects represent structurally. Sedna and 2012 VP113 occupy a zone that sits between 2 worlds. They are too far from the scattered disk to belong to it. They are too close and too structured to belong to the hypothesized Oort Cloud. The vast spherical shell of cometary bodies believed to exist at distances of tens of thousands of astronomical units. They sit in the middle, a transitional zone. The first signs of a transition from the inner solar system's flattened, planar geometry to the outer solar system's full 3-dimensional sphere. The inclination diversity among detached objects is already higher than among Kuiper Belt objects. And the further out you go, the more spread the inclinations become. The transition from flat to spherical does not happen at a sharp line. It happens gradually, layer by layer, as Neptune's organizing grip fades and the other influences take over. What was a flat disk becomes a thickening donut, and the donut becomes a sphere. Sedna and 2012 VP113 live in the region where that transformation is underway. How large is this detached population? The honest answer is that we do not know. We have found very few members, but the same observational bias that plagues the scattered disk applies here, multiplied. Most surveys concentrate near the ecliptic. Detached objects spend the vast majority of their orbital time far from the ecliptic, and their orbits are so large that even near perihelion, they are faint and slow-moving, easy to miss. The objects we have catalogued are almost certainly a small fraction of what exists. The deep outer solar system is being shaped by something the inner solar system does not feel. passing stars, galactic tides, or something still unseen. The orbit of Sedna alone is enough to establish that. Neptune did not do this. The known planets did not do this. Whatever did is either ancient and gone, or ongoing and invisible to us, or waiting to be discovered. And one of those possibilities, the third one, may not be invisible for much longer. Turn the telescope around for a moment. Stop looking outward at the distant orbits we can barely trace. Watch instead what comes in. Every year, new comets fall toward the sun from the outer solar system. They arrive with bright tails, burning off ice and dust as they swing close to the solar heat. They look like individual events, dramatic and unpredictable. But taken together, the directions from which they come tell a story far more important than any single comet's arrival. They are messengers, and the pattern of their messages reveals the shape of the place they left. To read that pattern, you have to divide comets into two groups. The division is simple on the surface. Short-period comets complete their orbits in less than 200 years. Long-period comets take more than 200 years, sometimes millions of years, to complete a single loop around the sun. But the difference is not only in time, the difference is in direction. Short-period comets are well-behaved by the standards of the outer solar system. Most of them originate in the Kuiper Belt and the scattered disk. They travel on orbits that stay relatively close to the ecliptic, generally within about 30 degrees of Earth's orbital plane. That tells you something. It tells you their source has a preferred orientation. A disk-shaped source, tilted populations and all, still produces objects with a recognizable bias toward the flat. Short-period comets carry the geometry of their origin zone with them. Then there is Halley's Comet. Halley does not behave like a short-period comet should. Its orbital period is roughly 75 to 79 years, well inside the 200-year threshold. By that measure, it belongs with the short-period group. But the answer was stranger than expected. Halley's orbital inclination is approximately 162 degrees. That number requires a translation. An inclination above 90 degrees does not mean a slightly steep orbit. It means the comet orbits in the opposite direction to the planets. While every major planet travels counterclockwise as seen from above the ecliptic, Halley travels clockwise. Retrograde. It moves against the stream. A 162-degree inclination is nearly as retrograde as it is possible to be. And that retrograde motion is a signature. It says the Kuiper Belt, which produced the other short-period comets, almost certainly did not produce Halley. Its origin was somewhere farther out. Somewhere with no preferred direction at all. That somewhere is what long-period comets come from. Long-period comets take more than 200 years per orbit. Many take thousands of years. Some have orbital periods measured in the millions. They fall in from the deep outer solar system, from distances that dwarf the scattered disk and the detached objects we have already traced. And when you measure the inclinations of long-period comets, they do not cluster near the ecliptic. They do not favor any angle at all. They span the full range from 0 degrees to 180 degrees. Prograde and retrograde. Above and below the plane. Every angle in every direction in roughly equal proportions. That is not a coincidence. That is a fingerprint. Think about what a flat source produces. If long-period comets were falling inward from a disk, a reservoir concentrated near the ecliptic, their inclinations would cluster. Most would arrive from near the plane. A few would be scattered, but the distribution would be skewed. You would see a preference. There would be a direction that the comets favored. There is none. The distribution is isotropic, all directions equally represented, random to any measurement we can make. A random distribution of arrival directions can only come from a source that has no preferred direction itself. Not a disk, not a ring, not a thick donut, a sphere. If you send objects falling inward from every point on the surface of a sphere, those objects will arrive from every direction with equal probability. The arrival pattern of long-period comets maps the shape of their origin region, and that shape is spherical. This was one of the first and strongest arguments for the existence of the Oort Cloud. The Oort Cloud is a hypothetical vast shell of icy bodies surrounding the solar system at enormous distances, tens of thousands of astronomical units from the Sun, far beyond the scattered disk and the detached objects. We cannot image it directly. No probe has reached it. No survey has catalogued its members from a distance. But the comets it sends inward carry its signature. They arrive from every direction, isotropically. And an isotropic source must be a sphere. The logic is elegant in its simplicity. You do not need to see the source. You only need to watch the direction from which the messengers arrive. If they come from everywhere equally, the reservoir is spherical. Not probably spherical, not approximately spherical. Spherical. The geometry of the arrivals forces the conclusion. Jan Oort, the Dutch astronomer who formalized this argument in 1950, was working from exactly this reasoning. He looked at the orbital data for long-period comets. He noticed the isotropic distribution. He worked backward from that distribution to the shape of the source. The cloud that carries his name is, to this day, inferred primarily from this evidence, not from direct observation, from the pattern the comets make when they fall in. Think about that for a moment. We are describing the shape of a structure that no instrument has ever seen by reading the directions of objects it has sent inward over billions of years. The comets are not dramatic because they are bright. They are remarkable because they are evidence. Each one is a data point. Each one confirms that its origin has no preferred plane. The solar system contains a spherical shell. That shell is the outermost reservoir. Its shape was written in the sky long before we understood what we were reading. What remains is to understand what that sphere is made of, how it formed, and whether anything out there is disturbing it. Those questions are still open. But the shape itself is not a guess. The comets settled that. And the comets are not the last word on what the outer solar system contains. But the orbits themselves have more to say. We have traced the pattern outward. Planets nearly flat. The asteroid belt tilted further. The Kuiper Belt puffed into a thick donut. The scattered disk dispersed across a vast volume. The detached objects sitting in silence far beyond Neptune's reach. And then, the comets, arriving from every direction, mapping the outline of a sphere we have never seen. Each layer adding another degree of departure from the familiar flat picture. Now consider the individual objects sitting at the most extreme end of that departure. Not the ones tilted by 10 degrees, or 20, or even 40. The ones that have been turned completely upside down. In 2008, astronomers discovered a small trans-Neptunian object and gave it the formal designation 2008 KV42. They nicknamed it DRAC. Its orbital inclination is approximately 104 degrees. That number needs a moment to settle. An inclination above 90 degrees means an orbit that runs opposite to the direction of planetary travel. Not tilted, not steep, reversed. DRAC does not orbit the Sun the way Earth does, the way Jupiter does, the way Neptune does. It orbits backward, cutting across the solar system in the opposite direction from nearly every other body in it. This is not a modest departure from the flat picture. This is an orbit that has been completely inverted. Producing an orbit like DRAC's requires more than ordinary planetary perturbation. A close gravitational encounter with Neptune can push a body into a steep incline, but to push it past 90 degrees, to actually reverse its orbital direction, demands something more extreme. Scientists have identified 3 candidate mechanisms. The first is the slow accumulation of inclination changes through repeated interactions with Neptune over hundreds of millions of years. Each encounter nudges the orbit a little further. Over enough time, the nudges can compound into a full reversal. The second is a close pass from a nearby star in the early solar system. A stellar intruder moving through the outer solar system billions of years ago could have delivered enough gravitational impulse to redirect distant bodies into entirely different orbital planes. The third is the galactic tide. The galactic tide is the combined gravitational influence of all the matter in the Milky Way, acting differentially on the solar system's outermost bodies. The stars, gas, and dark matter of the galaxy pull slightly harder on the near side of a distant orbit than the far side. Over the full age of the solar system, that differential pull acts like a slow tide, gradually tugging orbital planes in new directions. For bodies close to the Sun, this effect is completely negligible. Solar gravity dominates. But for objects at hundreds or thousands of astronomical units, the Sun's grip weakens enough that the galactic tide becomes a meaningful force. It may be one reason the outer solar system contains orbits at every possible angle, including angles that point backward relative to the planets. Drac may be a transitional object. It may have started its life somewhere in the scattered disk or the Oort Cloud, and been progressively twisted into its current configuration over billions of years of accumulated perturbation. The precise pathway is still being studied, but the destination is clear. The solar system contains orbits at literally every inclination from 0 degrees to 180 degrees, from perfectly flat to completely inverted. Drac is not an anomaly that contradicts the structure. It is the logical endpoint of the gradient we have been tracing since the asteroid belt. The dwarf planets confirm the trend in a quieter way. Makemake was discovered in 2005. Its inclination is approximately 29 degrees. Haumea, also discovered in 2005, orbits at approximately 28 degrees. Gonggong has an inclination of about 30.7 degrees. None of these are retrograde. None of them approach the extremity of Drac. But each one sits well off the ecliptic, and each one reinforces the same pattern. The farther you go from the Sun, the more inclined the typical orbit becomes. The ecliptic's pull fades gradually, and the range of possible angles widens to fill the space it leaves behind. The physical reason is straightforward. Closer to the Sun, solar gravity is strong and orderly. The giant planets add their influence. Together, these forces press orbits toward a common plane. Perturbations happen, but the dominant gravitational environment pushes back against them. Bodies that drift too far off plane get tugged and jostled back toward the ecliptic region over time. The system maintains its flatness because the forces maintaining it are powerful and persistent. But farther out, that dominance weakens. The Sun's gravitational control falls off with distance. The giant planet's reach fades, and the small, cumulative forces that barely register in the inner solar system, passing stars, the galactic tide, distant unseen masses, begin to matter. Perturbations accumulate rather than damp out. Orbits drift. Inclinations grow. The disk does not end at some sharp boundary. It inflates. Gradually, from a flat disk at the center to a thick donut in the Kuiper Belt, to a dispersed cloud in the scattered disk, to a fully inverted orbit like Drac's, to a sphere at the outermost edge. The solar system puffs up slowly, layer by layer, as the Sun's grip loosens. That is when the pattern broke. Even this picture, this gradient from flat to spherical, may not be the complete story of the outer solar system's structure, because there is one more puzzle sitting inside the scattered disk and the detached population. One more piece of evidence pointing towards something we have not yet found. In 2016, astronomers Konstantin Batygin and Mike Brown published a paper presenting a specific observation and a specific explanation for it. They had examined the orbital parameters of several distant trans-Neptunian objects. Not their distances, not their sizes, but the orientations of their orbits. The direction each orbit points in three-dimensional space. And they found something unexpected. Those orbits were clustered, not randomly distributed across all possible orientations the way a dynamically chaotic outer solar system would produce. Grouped, aligned, pointing in roughly the same direction. Random perturbations do not do that. Stellar passes and galactic tides, acting independently over billions of years, tend to scatter orbital orientations widely, not concentrate them. Something would need to be actively shepherding these distant objects, gravitationally nudging them over time into a shared configuration. Batygin and Brown proposed an explanation. A large planet, undiscovered, in the deep outer solar system, a body with a mass somewhere between 5 and 10 times Earth's mass, orbiting the Sun at a distance of roughly 400 to 800 astronomical units, far beyond even Sedna's perihelion, tilted at approximately 15 to 25 degrees from the ecliptic. If it exists, Planet 9 would be one more massive body confirming what the entire outer solar system has been saying for decades. Not flat, not contained, not simple. A world orbiting far beyond any of the 8 familiar planets at a distance so extreme that it has never been seen despite multiple dedicated searches. It has never been directly observed. The evidence for its existence remains entirely indirect. The orbital clustering is real and measurable. What produced that clustering is still an open question. Perhaps it is Planet 9. Perhaps it is a statistical artifact of incomplete surveys, a bias introduced because most observations concentrate near the ecliptic and miss the full distribution of distant objects. Perhaps something else entirely is responsible, some mechanism not yet identified. We do not know. What we do know is this. If Planet 9 exists at the parameters Batagian and Brown proposed, it breaks the flat picture one final time. Not as a curiosity, not as a borderline case, a planet 10 times Earth's mass, orbiting hundreds of astronomical units from the Sun, tilted well off the ecliptic, invisible to every telescope that has searched for it. Another massive body in a region the familiar diagram does not even acknowledge as existing. And the detached objects clustering around it, if that is what is happening, would be further evidence that the outer solar system is being shaped by forces the inner solar system cannot feel. 3 questions remain open. Does Planet 9 exist at all? If it does, where exactly is it? And if it does not, what else produced the clustering? Those questions are still being worked. The searches are ongoing. The answers have not arrived. The Oort Cloud is still waiting beyond all of this. Step back far enough, and the planets disappear. Not just become small. Disappear. They shrink below the threshold of relevance, and something else takes their place. Something the diagram has never shown. Something most people have never pictured when they think about the solar system at all. Let's think about the journey outward in steps. Mercury orbits at about 0.4 astronomical units from the Sun. Neptune, the outermost planet, orbits at roughly 30 astronomical units. That is the span of the familiar solar system. Everything taught in school, everything drawn on classroom walls. The Kuiper Belt extends the picture a bit further, out to roughly 50 astronomical units. Sedna, the detached object with the most remote known orbit, reaches an aphelion of about 937 astronomical units. Those numbers feel large. They are not. Not compared to what comes next. The inner edge of the Oort Cloud begins somewhere between 2,000 and 5,000 astronomical units from the Sun. The outer edge reaches somewhere between 50,000 and 100,000 astronomical units. At its outermost boundary, the Oort Cloud sits roughly 1.6 light-years from the Sun. Proxima Centauri, the nearest star to our own, is about 4.24 light-years away. That means the Oort Cloud reaches approximately 40% of the way to the nearest star. Think about that for a moment. The solar system does not end near the planets. It does not end at the Kuiper Belt. It extends nearly halfway to another star. Here is the analogy that makes this concrete. If Neptune's orbit were shrunk to the size of a quarter, roughly 2.5 centimeters across, the outer edge of the Oort Cloud would sit about 80 meters away. That is roughly the length of a football field. The quarter is at one end. The Oort Cloud's boundary is at the other. And everything you have ever thought of as the solar system, every planet, every moon, every asteroid belt, every Kuiper Belt object, everything is contained within that tiny coin. Not an exaggeration, not approximately true, precisely, measurably true. The man who first argued this was Dutch astronomer Jan Oort. In 1950, Oort examined the orbital data for long-period comets, those with orbital periods exceeding 200 years, sometimes millions of years. He noticed something that the data made hard to ignore. Many of these comets appeared to originate at enormous distances from the Sun, in the range of 20,000 to 100,000 astronomical units. And they arrived from every direction, not clustered near the ecliptic, not concentrated in any preferred region of sky, from every angle, equally. That pattern had a clear geometric implication. A flat or disc-shaped source would produce arrivals clustered near a preferred plane, just as the short-period comets from the Kuiper Belt cluster near the ecliptic. An isotropic arrival pattern, spread equally across all directions, can only arise from a source that is itself isotropic, spherical, surrounding the Sun on all sides. Therefore, Oort concluded, the solar system is enclosed by a vast spherical shell of icy bodies, one that sends comets falling inward from every direction, carrying no memory of any preferred plane. It was a logical argument built from arrival angles, not a direct observation, and that distinction matters, because no Oort Cloud object has ever been directly observed in place. Every piece of evidence for the Oort Cloud is indirect, carried inward by the comets themselves. We have never seen it. We have only read its signature in the paths of objects that fell away from it. The structure is believed to have two components. The outer Oort Cloud spans roughly 20,000 to 100,000 astronomical units. Orbits there are essentially randomly oriented. Inclinations range from 0 to 180 degrees, prograde and retrograde in equal measure, pointing in every direction with no preference for the ecliptic or any other plane. This is the reservoir for most long-period comets. The inner component, sometimes called the Hills Cloud, after astronomer Jack Hills, who proposed it in 1981, spans roughly 2,000 to 20,000 astronomical units. It is denser than the outer cloud. It may retain a slight flattening, a residual echo of the disk that formed everything else, but it is still enormously more three-dimensional than the Kuiper Belt. It serves as the transitional zone between the scattered disk and the full spherical geometry of the outer cloud. The composition of both regions is similar to that of comets: water ice, frozen methane, frozen ammonia, frozen carbon dioxide, rocky dust. Most objects are a few kilometers across. Some may be considerably larger, dwarf planet-sized bodies too faint and too distant to have ever been detected. And there are a great many of them. Estimates for the outer cloud range from several hundred billion to roughly 2 trillion objects larger than 1 kilometer across. The inner cloud is thought to hold 5 to 10 times more. Total population, possibly several trillion objects, spread across a total mass somewhere between 1 and 40 times the mass of Earth. Though that range reflects genuine uncertainty. No one has counted them. No one can. The volume they occupy is staggering, roughly 4.2 times 10 to the 42nd power cubic kilometers, a number that does not map onto any household object. It simply dwarfs everything else in the solar system by a factor of millions. The picture did not hold. Despite trillions of objects occupying that incomprehensible volume, the Oort Cloud is almost perfectly empty. The average distance between objects is tens of millions of kilometers. If you were somehow placed inside the Oort Cloud, you would see nothing around you. No neighbor bodies, no glow of a crowded region. The Sun itself would be reduced to a moderately bright star, no more conspicuous than several other nearby stars in the sky. You would have no way of knowing, from visual inspection alone, that you were inside a solar system at all. Not crowded, not dense, profoundly, immeasurably sparse. Now comes the central reveal that all of this has been building toward. The solar system you have pictured your entire life, the flat diagram with the 8 planets arranged on a single plane, is the thinnest inner kernel of a vastly larger spherical structure. The planets occupy a disk roughly 300 times wider than it is thick. The Oort Cloud encloses that disk inside a sphere extending 100,000 astronomical units in every direction, above and below the ecliptic just as much as along it. What lies directly above the ecliptic at Oort Cloud distances is just as much solar system as what lies along it. The flat diagram does not merely underrepresent the outer solar system. It misses more than 99% of the solar system's spatial extent entirely. Not a slight omission, not an understandable simplification, a fundamental misrepresentation of the shape of the thing. The solar system is not a disk. It is a sphere with a disc-shaped kernel at its center, where the sun's gravity and the initial geometry of the protoplanetary disk conspired to press everything into a common plane. But that influence fades with distance, past the scattered disk, past the detached objects, past everything that still bends toward a preferred plane. The geometry opens outward in all directions equally, and what you have is a sphere. We have never seen it directly. We know it from the comets it releases, each one a messenger carrying the geometry of its origin. And that geometry is spherical. Unmistakably, logically, necessarily spherical. What remains is the question of how this sphere came to be, and what forces continue to disturb it. Stay inside the sphere a moment longer, not rushing outward yet, just asking what moves it. At Oort Cloud distances, the objects are bound to the sun by the thinnest thread of gravity imaginable. The sun is 100,000 astronomical units away. Its pull is real, but barely. A nudge from almost any direction can be enough to change an orbit permanently. The first source of nudges is the simplest. Stars move. The sun's nearest neighbors are not fixed in place. They drift through the galaxy on their own paths, and occasionally one passes close enough to the outer solar system to shift the trajectories of loosely bound objects. Not a dramatic collision. Not an encounter you would notice from the inner solar system. Just a gravitational whisper, applied over millions of years, enough to send a distant body falling inward on a new path. That is how a long-period comet begins its journey. A nudge from a passing star, millions of years ago, slowly redirecting an object that had orbited quietly for billions of years before. The second source is stranger. The Milky Way itself pulls on the Oort Cloud, not uniformly. The side of the cloud facing the galactic center feels a slightly stronger pull than the side facing away. This differential, this uneven tug across the cloud's enormous span, is called the galactic tide. Think of it the way a large mass in the distance pulls differently on the near side of a ship than on the far side. Applied gently across tens of thousands of astronomical units, over millions and millions of years, this differential gradually rotates orbits. For the outer Oort Cloud, the galactic tide is not a minor player. It is the dominant perturbation, the primary sculptor. The third source is the rarest, and the most dramatic. Giant molecular clouds are enormous concentrations of gas and dust scattered through the Milky Way. They can contain hundreds of thousands of times the mass of the Sun. When the solar system passes near one, the gravitational interaction can be severe enough to send a whole wave of Oort Cloud objects inward at once. A cometary shower. Some researchers have suggested, cautiously, that such events may be connected to the mass extinction events in Earth's biological history. The timing, they argue, might line up with periods when the solar system passed through denser regions of the galaxy. But this connection is contested. The evidence is indirect. It remains a speculation, not a conclusion. The sphere, then, is not static. It breathes, it shifts, it sends objects inward occasionally, and those objects become the comets we see. Without that slow rain of disturbance, we would have no comets, and no evidence this structure exists at all. Now comes the question the script has been building toward since its first section. What is directly above the solar system? The answer depends on which solar system you mean. If you mean the region of the major planets, the solar system ends at roughly 30 astronomical units. That is where Neptune orbits. Beyond Neptune, the planetary solar system simply stops. If you mean the region where the sun's stream of charged particles, the solar wind, still fills space, the solar system ends at the heliopause. That boundary sits at roughly 120 to 140 astronomical units from the Sun. In 2012, Voyager 1 crossed that boundary. In 2018, Voyager 2 crossed it too. They became the first human-made objects to enter interstellar space by that definition. This was celebrated rightly as a monumental achievement. But the reality was different. Crossing the heliopause is not leaving the solar system, not gravitationally, not structurally. At current speed, Voyager 1 would need approximately 20,000 years to reach the inner edge of the Oort Cloud. And then it would spend tens of thousands of years more crossing the cloud itself before emerging from the solar system's gravitational domain entirely. Voyager 1 is in interstellar space by one definition. It is deep inside the solar system by another. If you mean the region where the sun's gravity still dominates, the solar system extends to the outer Oort Cloud. That is roughly 100,000 astronomical units. That is the real edge. And the real solar system, measured gravitationally, is approximately 2,000 times larger than the diagram you have seen in every textbook, every classroom, every museum display. Not a little larger, 2,000 times larger. From a vantage point directly above the sun, 100,000 astronomical units out, you would see very little. The sun would appear as a moderately bright star among others, no more remarkable than its nearest neighbors. The planets would be invisible. The Kuiper Belt would be invisible. The constellations would look almost the same, shifted very slightly by the 1.6 light years of displacement. Around you in every direction, the interstellar medium, averaging roughly 1 atom per cubic centimeter in our region of the galaxy. A density so thin, it would qualify as a hard vacuum by any terrestrial standard. You would be inside the local bubble, a low-density cavity roughly 300 light-years across, carved out by ancient supernovae over millions of years. The environment above the ecliptic at that distance would be identical to the environment alongside it. Equally empty, equally cold, equally solar system. Above the solar system is more solar system. Below it is more solar system. In every direction. But that is only the answer within one reference frame. The ecliptic has been the measure of above and below throughout this journey. But the ecliptic is one plane among several, and here at the outer edge of the solar system, another plane becomes impossible to ignore. The Milky Way has its own plane. The galactic plane, defined by the great flat disk of stars, gas and dust that forms the galaxy's visible structure. Roughly 100,000 light-years across, 1,000 to 2,000 light-years thick, containing somewhere between 100 billion and 400 billion stars. A barred spiral, our best measurements suggest, with a dense central bulge and long sweeping arms of stars. The Sun sits in a minor feature called the Horian Spur, a partial arm between two of the major spiral arms, about 26,000 light-years from the galactic center. Not at the center, not at the edge, a quieter region, which is perhaps part of why the inner solar system has remained stable long enough for life to appear. Now, consider the relationship between the two planes. The ecliptic and the galactic plane are not aligned. They are tilted relative to each other by approximately 60 degrees. Think of a dinner plate lying flat on a table. That is the galactic plane. Now lean another plate against the wall at a steep angle. Not vertical, not horizontal, but propped up at roughly 60 degrees. That is the solar system's disk, tilted sharply against the galactic table. Ecliptic north, the direction perpendicular to Earth's orbit, and pointed up by convention, aims toward the constellation Draco. Galactic north, the direction perpendicular to the Milky Way's disk, aims toward the constellation Coma Berenices. These two norths are separated by approximately 60 degrees of sky. They are not the same direction. The up of the solar system and the up of the galaxy point to different places. The Sun is currently about 50 to 80 light-years above the galactic midplane, inside a disk 1,000 to 2,000 light-years thick. This is barely a displacement, essentially centered. But the Sun does not stay at any fixed height. It bobs. Like a horse on a carousel, rising and falling while the carousel turns, the Sun oscillates up and down through the galactic midplane. The amplitude of that oscillation is roughly 200 to 300 light-years. The period is roughly 60 to 70 million years. The Sun is currently near the midplane, slightly above it, moving upward. Some researchers have noted speculatively that periods when the solar system sits near the galactic midplane where the density of stars and gas is higher, may correspond to periods of increased Oort Cloud disturbance, more cometary showers inward, and possibly higher rates of impacts on Earth. The timing, they suggest, might correlate with some of the great extinction events in Earth's biological history. This connection is unproven, the evidence is indirect, and the causal chain is long. But it is the kind of question that sits quietly at the edge of what we know, waiting for more data. Travel upward from the galactic plane, perpendicular to the disk, and you pass through layers. First, the thin disk, the densely populated flat band of stars, gas and dust, where most of the Milky Way's visible mass lives. Then, the thick disk, older and more diffuse, extending perhaps 3,000 light-years above and below the midplane. Then, the stellar halo, a roughly spherical region tens of thousands of light-years from the plane, populated by ancient stars more than 10 billion years old, metal-poor relics from the early universe. Scattered through the halo are the globular clusters. About 150 are known to orbit the Milky Way. Each is a dense sphere containing hundreds of thousands of stars, packed tightly enough that the night sky from inside one would be extraordinary, full of nearby suns in every direction. They are old, typically 10 to 13 billion years old. Like ornaments hanging on a tree, they orbit throughout the halo, some tens of thousands of light years from the galactic plane. Beyond the stellar halo, invisible to any telescope, is the dark matter halo, roughly spherical, extending perhaps 600,000 light years from the galactic center. We have never seen it. We know it exists because the outer stars of the Milky Way rotate faster than the visible matter alone could explain. Something invisible provides the additional gravitational mass. Whatever dark matter is, it constitutes most of the galaxy's total mass, holding everything else together. And then, finally, intergalactic space. The density there is approximately 1 atom per 10 cubic meters, not per cubic centimeter, not per cubic millimeter. Per 10 cubic meters, roughly the volume of a modest room, the emptiest environment in the known universe. From that distance, looking back, the Milky Way would appear as a luminous disk, spiral arms faintly visible, central bulge glowing, halo barely detectable. The solar system would be invisible. Earth would be undetectable by any instrument yet built. Looking outward, other galaxies. Andromeda, approximately 2.5 million light-years away, the largest neighbor in our local group. The Magellanic Clouds, smaller satellite galaxies visible from the southern hemisphere. Dozens of dwarf galaxies scattered around the Milky Way's periphery. And the Milky Way itself is not stationary. The entire galaxy falls toward the center of the Laniakea supercluster, a vast gravitational basin containing hundreds of galaxies, including the Milky Way, at roughly 600 kilometers per second relative to the cosmic microwave background radiation. That motion produces a faint imbalance in the microwave background, a slight blue shift in the direction we are falling, a slight red shift behind us. This imbalance defines yet another direction, another reference frame, another version of forward and back. Every frame is real, none is absolute. The ecliptic gives one definition of above and below. The invariable plane, perpendicular to the solar system's total angular momentum, gives another, tilted roughly 1.6 degrees from the first. The galactic plane gives another, tilted 60 degrees from the ecliptic. The plane of the local group gives another. The direction defined by the Laniakea supercluster's gravitational pull gives another. The CMB dipole gives another still. Einstein's general relativity is clear on this point. There is no absolute coordinate system painted on space, no cosmic grid, no universal north. Directions are meaningful only relative to something. The moment you step away from any single massive object, no direction is preferred over any other. The flat diagram was not exactly wrong, but it was profoundly incomplete. The structures it represents are real. The planetary disk is real, pressed flat by the geometry of formation. The Kuiper Belt's cold core is real, thin and nearly flat. The hot scattered populations are real, tilted and dispersed. The Oort Cloud is real, a sphere enclosing everything, extending to the limit of the sun's gravitational reach. The galactic disk is real, tilted 60 degrees from the plane of your orbit. The halos are real. The dark matter is real. The intergalactic voids are real. What is not real, in any absolute sense, are the labels: above, below, up, down. These are gifts from biology, from the experience of living under gravity on the surface of a planet with a clear distinction between the ground and the sky. They are the most fundamental spatial words in any human language, and they simply do not map onto the geometry of the cosmos. When you stand outside at night and look up, you are not looking up. You are looking out, in one particular direction, from a small planet near the edge of one disc-shaped structure tilted at 60 degrees inside a much larger disc-shaped structure. Inside a roughly spherical cloud of solar material that extends nearly 2 light years in every direction. Inside a galaxy surrounded by a halo of ancient stars and invisible mass. Inside a supercluster falling through a universe that has no ceiling, no floor, no preferred orientation, and no absolute sense in which any direction deserves to be called up. The structures are real. The journey through them was real. What dissolves at the end of it is not the solar system. What dissolves is the certainty that the words we use to describe it were ever quite accurate enough,